donut because I wanted the champagne and the cake. I just thought that the donut would be just a little bit too much. Hello. This algebra workout is all about proof by mathematical induction. We've got two problems to solve, and here they are.
The first one is to prove that this sum, sigma from r equals 1 to n of r squared, is equal to this formula. That's 1/6 n multiplied by n plus 1 times 2n plus 1. And that's for all integers n greater than or equal to 1. So for n equals 1, n equals 2, and so on. The second problem is to prove that this inequality, that's 2 to the n, is strictly greater than n squared. And that's got to be proved for all integers greater than or equal to 5. So for n equals 5, n equals 6, and n equals 7, and so on. Well, both these assertions that I've been asked to prove are propositions that depend on the variable n, and that's an integer variable. So each of these would be called a variable proposition. So, for example, this first problem says that the sum 1 squared plus 2 squared plus and so on, up as far as n squared, is equal to the expression on the right. And remember, that's got to be true for all integers greater than or equal to 1. So actually, it is many, many statements all rolled into one, this variable proposition. On the other hand, problem 2 says that the inequality 2 to the n is greater than n squared is true for all integers greater than or equal to 5. Now, it may be true for some other integers as well, but we're only asked to prove that it's true for integers greater than or equal to 5. Well, one technique that can often be used to prove variable propositions is the technique of mathematical induction.
Well, first of all, let's introduce a piece of notation, and that's p of n. Well, this looks very much like a function, but p of n stands for a proposition. That's a mathematical statement that may or may not be true, a proposition involving n. Let me give you an example. For example, 2 to the power of n is greater than n squared for all n greater than or equal to 5. Now, that's a proposition involving n. I don't know whether it's true or false. But this technique of mathematical induction will prove it for us, and it works as follows. Well, let's start with the simplest case used to prove propositions for integers greater than or equal to 1. Now, we don't always start at 1. For example, we'll come to the greater than or equal to 5 case later. Well, if we know firstly that the proposition p of 1 is true, that's the proposition that you get when you substitute n equals 1, and it's the first thing you have to check. And secondly, that if p of k is true, then p of k plus 1 will also be true for all k greater than or equal to 1. That means that p of k implies p of k plus 1 is true for all k greater than or equal to 1. Then, if we know both of these, then we can say that p of n is true for all n greater than or equal to 1. That's really complicated, but you can see how it works on my magic board. This is p of 1, p of 2, p of 3, and we would go on forever. Now, using A, we prove that p of 1 is true. And because of B, that would imply that p of 2 would be true. And that with the knock-on effect would be that p of 1 true makes p of 2 true. However, p of 2 true proves that p of 3 is true, again using B. So the knock-on effect is that p of 3 is true. And this would go on and on. P of 3 being true would imply that p of 4 is true, then that p of 5 is true, etc., etc. So that's the general idea of mathematical induction.
So mathematical induction is a little bit like dominoes. Here's a line of dominoes, and I've set them up so that each domino will hit the next one if it falls over. Now, suppose that the first domino represents a proposition that's either true or false. If it's false, it has to remain standing. But if it's true, you can knock it over. The knock-on effect of a true domino falling over is that the next domino in line is also true. Establishing that the knock-on effect is valid and that the first domino is true means that we can prove that all the dominoes are true. So let's use mathematical induction to solve the first problem. Well, the variable proposition p of n here is this statement, that the sum from r equals 1 to n of r squared is equal to 1/6 n multiplied by n plus 1 times 2n plus 1, and that's for all integers, all n greater than or equal to 1. So let's go through these stages. Step A is to check that p of 1 is true, and step B is to check that p of k implies p of k plus 1, and that's for all k greater than or equal to 1. So let's begin. For step A, we have to substitute n equals 1 into this equation and see if it is true. So that gives me 1 squared on the left-hand side and 1/6, 1 multiplied by, well, 1 plus 1 and 2n, so that's 2 plus 1. So let's work this out and see if it is true. So 1 squared, well, that's just 1. And on this side, we have 1 plus 1, that's 2. 2 plus 1 is 3, so 2 3s are 6. 6 divided by 6 equals 1. So yes, it is true. So now we've got to check step B. If p of k is true, then p of k plus 1 will be true for all k greater than or equal to 1. So let's write down what it means for p of k to be true. Well, it means that 1 squared plus 2 squared plus and so on in the sequence up to k squared is equal to, and here we're just substituting in k for n, so that's 1/6 k multiplied by k plus 1 multiplied by 2k plus 1. Now we want to deduce p of k plus 1, so we'd better write down what that means as well. Well, p of k plus 1 means that 1 squared plus 2 squared plus and so on plus our k squared term plus the next one in the sequence, so that's plus k plus 1 all squared, is equal to, and here we're just substituting in a k plus 1 every time we had a k. So that's 1/6 k plus 1. And here for this bracket, well, k plus 1 plus another 1, that's k plus 2. And here 2k plus 1, well, that's 2k plus 2 plus another 1, so that's 2k plus 3. So we want to assume the first one, p of k, and deduce the second one. Well, if the first one is true, we could add k plus 1 squared to the left-hand side, and that would be the next element in the sequence. But we'd also, of course, have to add k plus 1 squared to the right-hand side. Well, if we did that, we'd get 1 squared plus 2 squared plus and so on plus k squared plus k plus 1 all squared. And that would be equal to this plus k plus 1 squared, so I'll write that in. That's 1/6 k multiplied by k plus 1 times 2k plus 1 plus k plus 1 all squared. Well, how can I rearrange this? Well, I can see that in this expression, there's a factor of k plus 1, so I'm going to start with that. So I'll bring k plus 1 here to the front, and that leaves me with k multiplied by 2k plus 1, this bracket, plus, well, I've taken out one lot of k plus 1, so that leaves me with k plus 1 here. But I also need to add a 6 before this bracket to balance out the 1/6 at the front there. Well, now I'm going to multiply out these brackets here just to make this a little bit easier to look at. So that's 1/6 k plus 1. Well, k multiplied by 2k, that gives me 2k squared, plus k, plus another 6k here, so that's plus 7k, and plus 6. And now the only question is, can I factorise this to get k plus 2 multiplied by 2k plus 3? Well, yes, I can. You only have to multiply this out to check that that works OK. So I have deduced that p of k implies p of k plus 1, and that that was true for all k greater than or equal to 1. So now I've checked A, and I've checked B. So I can deduce by mathematical induction that sigma from r equals 1 to n of r squared is indeed equal to 1/6 n multiplied by n plus 1 times 2n plus 1 for all integers greater than or equal to 1. Alan.
Phew. And you can use this method to evaluate many sums of this type. For example, You could do this one. The sum of 1 plus 2 plus 3 up to n is equal to n over 2 times n plus 1. Or something like this. The sum of 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed is n squared over 4 times n plus 1 all squared. So mathematical induction can be used to prove the formulas like this for many sums of this type.
Well, let's have a look at that second problem. That's 2 to the n is greater than n squared for all n greater than or equal to 5. Now, this is a little bit different from the first one. It's an inequality instead of an equality. But also, we're being asked to prove it from 5 onwards, not from 1 onwards. OK, we have our line of dominoes standing up again. And we're not going to knock over the first one. We want to knock over the 5th one. But before we can do that, we're going to need to use a method that's very similar to the one we did previously. But it's called generalised mathematical induction.
Yes, and generalised mathematical induction is very similar and is used when we're not necessarily starting at 1. But stage A is that instead of checking that P1 is true, we check that some other value, P of capital N, is true. And in Sarah's case, capital N is going to be 5. And then we have to check that the implication, P of K, true, would imply that P of K plus 1 is true for all K greater than or equal to capital N. And if A and B are both true, then the proposition is true for all n greater than or equal to the capital N where we started off. And then showing the dominoes again, we start with P of capital N, and by all the arguments you saw earlier on, if P of capital N is true, P of n plus 1 will be true, etc., etc. And the whole thing will fall down.
So I'm using generalised mathematical induction, and in this case, P of n, the variable proposition, is this inequality. 2 to the n is strictly greater than n squared, and that's for all n greater than or equal to 5. So for n equals 5, n equals 6, n equals 7, and so on. Well, before we start, I think it's a good idea to look at the values of these expressions, 2 to the n and n squared. And we've worked out some of these already.
And here are the values. Well, the question starts at n equals 5, so let's take a look. Well, if n is 5, 2 to the n, 2 to the 5 would be 32. And n squared, that's 5 squared, would be 25. And using similar arithmetic for n 6, 7, 8, 9, that's as far as this table goes. So, is our inequality correct? Is 2 to the n greater than n squared? Well, it is when n is 5, because 32 is greater than 25, so we can tick that one. And in fact, 64 is greater than 36, we can tick all the others, and we could indeed go on and on forever.
Right, let's apply generalised mathematical induction. So step A is to check P of 5. Then step B is to check that P of K implies P of K plus 1. And that's for all K greater than or equal to 5. So let's begin with step A. If I take n equal to 5, well, that gives me 2 to the power 5 greater than 5 squared. Is that the case? Well, 2 to the power 5, that's 2, 4, 8, 16, 32. And 5 squared, that's 25. So that is true. And we saw that in Alan's table. So now for step B, which we always expect to be a little bit harder, we have to check that P of K implies P of K plus 1 for all K greater than or equal to 5. Well, let's write down what those two statements are. So P of K is 2 to the K greater than K squared. And P of K plus 1, well, we're just substituting in K plus 1 every time we've got a K. So that becomes 2 to the K plus 1 is greater than K plus 1 all squared. Well, it's convenient in this case to rearrange these inequalities to get everything over onto the left. So that's 2 to the K minus K squared is greater than 0. And this one, 2 to the K plus 1 minus K plus 1 all squared, again is greater than 0. It's often a good strategy to rearrange an inequality. It doesn't always help, but here it does. So we know this, and we want to deduce that. So let's use the fact that 2 to the k plus 1 is 2 times 2 to the k. And so I could rewrite this second inequality as 2 to the k plus 1 minus k plus 1 all squared. That would be the same as 2 multiplied by 2 to the k minus k plus 1 all squared. So we've just substituted in 2 times 2 to the k for 2 to the k plus 1. But we also know that 2 to the k is greater than k squared. Substituting in k squared for our 2 to the k, well, that means that I could rewrite this as 2 times k squared minus k plus 1, all squared. And we know that this would be greater than this new expression because 2 to the k is greater than k squared. Now it's a question of using some algebra. Well, this is algebra workout to rearrange this expression on the right-hand side. So I'm going to multiply out this square and collect the like terms. And what I get is that that's equal to k squared minus 2k minus 1. Now what we'd like to prove, remember, is that that's greater than 0. Well, when you just look at it, you can't really see that it's greater than 0, but if I complete the square, which is always a good thing to think of doing, I get k minus 1 all squared, and then I have to balance that by taking away 1, so I get minus 2. And now I'm going to test this by substituting k greater than or equal to 5. Well, if I do that, I get 5 minus 1, that's 4. 4 squared is 16 minus 2. So this is greater than or equal to 14, which is strictly greater than 0. So I verify that if I assume p of k, then I can deduce p of k plus 1. So that completes step B of the generalised mathematical induction. So I can deduce that 2 to the n is greater than n squared for all n greater than or equal to 5. And so using our dominoes analogy, I am able to knock them down from the 5th one onwards.
Well, this method of generalised mathematical induction can be used to prove, well, lots of other inequalities. For example, that n factorial is greater than 10 to the n for all n greater than or equal to 25. But we're not going to try that one in this programme. Well, that's all from this edition of Algebra Workout, which is in fact the last edition of Algebra Workout. Good luck with the rest of the course, and of course, good luck in your final exam.
Goodbye.
Goodbye.